Okay, so welcome back, and we continue our topic, which is the Rademacher complexity and the growth function and VC dimension. So that's chapter 3, which is this. Rademacher complexity. Growth function and VC dimension. As I said, this chapter is in some sense talk about some very basic results which appear many times throughout the course and then in the textbook. And so where we are, we talked about the notion of Rademacher complexity, and we derived, so here's a reminder of what we covered so far. So we talked about Rademacher complexity and its definition. And important bit is we used it to provide a uniform generalization bound. So all these concepts are there to measure the complexity or expressiveness of a hypothesis class. And then we show that how this complexity measure can be used to derive an upper bound of the upper bound on the generalization error. Okay, so typical form of the upper bound is the one that we showed before. We showed the two upper bound with the Rademacher complexity, but the one that will appear today again is this form. Say the probability of 4 hypotheses the probability that its risk of generalization error is bounded by empirical error plus Rademacher complexity of hypothesis class with some slack, which is actually coming from the generalization bound and the use of concentration inequality. So it's really say we cannot really talk about the generalization error, but using this complexity measure, we can have an upper bound with high probability. So this one, the result say this one is greater than 1 over delta. Okay. And that will, in the next chapter, when we talk about structural risk minimization or empirical risk minimization, you will see the use of this this generalization bound. This is really about the quantity that we can measure, which is the right-hand side, and how we can use that quantity to talk about some quantity that we really care about, which is a generalization error. Okay, but these facts, especially the uniform upper bound, will be used to derive a guarantee of some quite abstract algorithm, machine learning algorithm, well, very abstract strategy of designing machine learning algorithm, which are empirical risk minimization and structural risk minimization. Okay, and then you see the importance of Rademacher complexity that appears here. And then, so this Rademacher complexity appears, that's because we want to state this type of the bound, not just a single hypothesis, but every hypothesis in our hypothesis class. And that's what we just derived. And we also derived something similar for empirical Rademacher complexity. Just write it here. So that one has empirical Rademacher complexity. maybe I just make it explicit. And the whole probability is about this sample. It's coming from distribution over M. Okay. And the exact notation that I used time was this one. They sampled have the list of XY pairs, and we only project the input components from that, and we compute the Rademacher complex with this guy. And then the extra slack was 3 times 2m over log of 2 over delta. So that was the result. But then we said this Rademacher complex is pretty good. I mean, it's bound quite tight, but it's hard to compute. So the quantity that we talked about, like this one and the one below, they are very informative, but they are at the same time difficult to compute. So what we want to have is something that is a bit easier to deal with. So here's the general strategy. We trade off expressiveness with the convenience for computation. So we come up with some complexity measure, which is more abstract. There was something called growth function. So Rademacher complexity depend on the distribution on inputs, but yeah, distribution on the input. Growth function doesn't depend on the distribution on the input. So it's, in a sense, a less informative concept, okay, for about the problem that we are dealing with. On the other hand, in doing so, we are getting something which is easier to compute or easier to deal with. So the definition of the growth function was this one. For if we have a hypothesis class H, the growth function on hypothesis class is a function that takes natural number to return the natural number union infinity. And it's defined like this. It's a hypothesis class F, the H, given M, set this primum over sample the x1 to xn. So you can choose any M sequence in the input space. Then compute the cardinality of all the labels that we can assign to these guys using some hypothesis. Okay. So use a hypothesis H, assign label to everyone. But instead of just using one hypothesis, we are considering all the hypotheses. And the specific context we are dealing with is for the context of the classification. So then H is a mapping from input to output is just -1 and +1. So +1 is something classified as positive, minus negative, so on. So in that case, one easy thing that you can see from this definition is that growth function is actually bounded. It's always a return a natural number that is bounded by 2 to the n. So what is the maximal case? Maximal case is for every for sample x1 to xm, if suppose they are all different, and if we can assign ±1 for the first guy, second guy, and so on, then we end up with a 2 to the n possibility, because each component we have 2 possibilities, and that's the maximum possibility we can get. So the growth function is bounded by 2 to the n. So in some sense, we say if the growth function for every m is exactly the same as 2 to the m, that means our hypothesis class is very expressive, which is a good, maybe a good thing or a bad thing. In terms of expressiveness, it's a good thing. In terms of computability, we're getting some guarantee, it's a bad thing, because it means that it's unlikely that we can get some benefit from good result about generalization. On the other hand, if the growth function, so So the growth, I mean, this is viewed from a picture. You can see that, I mean, we have exponential functions that grows like this. This is equal to m. I mean, it's written over the integers, but I just wrote, let me draw, it's a schematic diagram, which just shows the exponential growth. But if the growth function follow the exponential, but at some point it becomes linear like this. So then we can kind of see that we can kind of try to detect these points. And based on that detections, can kind of say that there is some, I mean, this hypothesis class that has a limited expressiveness. So how much that it diverged from the, I mean, from the maximum, that give an indication that how limited our hypothesis class is. And that becomes the source of generalization. And I didn't prove the result, but I showed that there is using this growth function, we can get a generalization bound. So suppose either I can select this. Okay, I can't really do it. Okay. So we can get the same results, it's very similar results. So we can, but now we can give a upper bound, generalization bound in terms of the growth function. The form is always the same. The generalization error is bounded by the empirical error plus some quantity that measures the complexity of the hypothesis class. But this time, this complexity measure is going to be this one. Yes. Delta. So that's going to be the results that we're going to show in this part, okay, today. So by comparing these two, then you can see that what's really going on is we're going to show that this Rademacher complexity of a hypothesis class is going to be bounded by the quantity that I just wrote below. And so we can bound Rademacher complexity by using the growth function. Okay, so before going further, we may say, okay, so then what did we gain? What we gain is, as I said, Rademacher complexity on the above depend on the distribution, so it's a bit more complex quantity to deal with. On the other hand, the growth function. So in fact, the Rademacher complexity cannot be computed because we don't know the distribution. On the other hand, growth function doesn't really depend on the distribution at all. So that's the quantity, in theory, we can compute. And then in doing so, we can get a generalization boundary. So now the question is how we can show the key step. Is that the Rademacher complexity of each is bounded by square root of y1. So how we can prove this? So that's the main question that we will answer. Let's start with this part. So we show that generalization bound with growth function. And as I said, the key things that we care about here is Rademacher complexity H is bounded by the root of n to this is what we want to show. So that is what's written as a corollary. So if we show this, then by just combining what we already have with this corollary H, we can show the generalization bound that I showed in the previous slide. And then the generalization bound is written as theorem 3.9. Right. So how we can prove this quantity? And so let me start with a bit different way than what's presented in the textbook. So this is so-called corollary 3.8. But then now the question is how we can prove this corollary 3.8. 3.8. So here's a lemma that we're gonna use to prove this corollary 3.8. So actually in the textbook, I think it's written as a theorem. Or theorem. .7, that's called Massard lemma. What does the lemma say? It tried to tell us something that's related to the Rademacher complexity, which is the expectation of Rademacher variables with the quantity that appears in this in the growth function, which is in a sense the number of possible labelings that we can maximally give for certain input. Okay. So the lemma say the following. So it says that suppose that A, B, M real numbers, and then this be a finite non-empty. So if that we do so, and also that R is the maximum, because it's finite, we can talk about maximum of the size of Y with L to no. What does this mean? This means that maximum of YA or the coordinates yi square root. So that's what it means. If we do so, then we can show the following expectation. So then the following is true. Expectation of Riemann one over n Riemann of y in A sigma I. This is bounded by R times 2 log A divided by N. So then the expectation is over sigma, that is uniformly sampled, -1 and +1. Now, if you look at this property, this lemma, one thing that you can see is that this right-hand side looks a bit similar to what you appear in the Rademacher complexity. In the Rademacher complexity, this yi is obtained by applying some hypothesis to xi. But that is exactly saying something very, very close to say, we just take ith component of y. So this y is generated by applying specific hypothesis to every input x1 to xm. And the quantity that we are writing on the left-hand side is really the Rademacher complexity. And the quantity that we are writing on the right-hand side is a bit different. It's not about Rademacher complexity. It is about the size of all the possible labeling. So this is really the size of all the possible labeling that we can obtain by applying this hypothesis to the inputs. And then this R, which is a maximum. If you are familiar with, so what's really going on? You can ignore this 1 over m because it appears on both sides. So if you are familiar with so-called Cauchy-Schwarz inequality, if you are not familiar with Cauchy-Schwarz inequality, don't worry about it. So if you are familiar with Cauchy-Schwarz inequality, this is more like an analogy. So what Cauchy-Schwarz inequality tells us is say that if you have a very complicated quantity that involves, two things at the same time, AI, I is 1.1. So then that can be bounded by some quantity that you can compute separately. AI squared, sum of BI squared. And there are more complex inequality of that kind. But the spirit is the same. It's say that you have something that kind of connects AIs and BIs. Something similar is happening here. We have something that connects this yi, and then all the possible things in A. So the size of A and each specific value of yi, they are intertwined in the left-hand side. And the right-hand side, they separate them out. So for yi, the only information that we capture is it's a maximum norm. Okay? And then for A, the only information that we capture is its sign. So we want to separate out some intertwined information to two separate information. One is the size of A, and the cardinality of A. The other is actually that's a L2 norm of elements in A. And that's what this theorem tries to achieve us. What this theorem achieves. Okay. The complex quantity coming from the Rademacher complexity is bounded by R, which is a maximum of the L2 norm of elements in A times something related to the cardinality of A. Okay. So now, before proving this Massart lemma, let's use this Massart lemma and prove this our generalization bound. Let me mark. This is a lemma. And gonna prove this corollary, which is another on the top, and how we can prove. So the proof is not that complex. So we start with the Rademacher complexity. So by using lemma 3.7, it's easy. I mean, what we are doing is that essentially the theorem 3.7, left-hand side is very close to the Rademacher complexity. Right-hand side is something which, if you do some calculation, that's going to be closely related to the growth function. So that's why we can get a chloride 3.2. So let's see how it works. We start with the Rademacher complexity. That is expectation over so it's inputs of size m. And then it's an empirical Rademacher complexity that's defined by expectation of Rademacher variable. It's 1 plus 1. And then Spreeman hypothesis. Summation 1 over m. Summation of sigma I and h of xi. I is equal to 1/3. So what is xi? Xi is really the sample. S is written as x1 to xn. So that's just the definition of Rademacher complexity. So it's an average empirical Rademacher complexity that's written, but that's what I just wrote there. Now we do some simplification here. So now if you look at, this h together with h of xi, for each hypothesis, once sample x1 to xm is chosen, we are not really doing anything on this hypothesis other than just applying h to xi. Okay? So we can directly replace h to xi. So we're gonna use some notation. So that's our notation. We say for hypothesis restricted to S, that means each of these hypothesis restricted to S means that it's just a vector of h of x1 up to h of xm. So S is x1 to xm. Each hypothesis of h. So that's our notation. If you prefer, you can also view this as some h restricted to the domain S. You can view this as a function or vector. It doesn't really matter. They are equivalent. So now if we do this, so this becomes, all of a sudden, this becomes a finite set. And then each of these guys are m-dimensional vector. Okay. So it's an m-dimensional vector H, because x1 to xm are fixed. Each of hi is either plus minus 1. This is a finite set and m-dimensional vector. Exactly the setting where we can apply this Massat lemma. So now if we apply, so then first we write. Writing becomes so complex, but we write the quantity there. Then we have expectation S and expectation sigma together with Spreeman of, let's call it Y, H restricted to S, 1 over M, sigma I is equal to 1 to M, sigma I, 1I. Now we can apply the Massat lemma to the theorem 3.7. We apply the theorem 3.7, this is what we're going to get. Here we have something called R divided by n square root of 2 to the log of, A is the set, H restricted to S. Now the question becomes, what is R? R is the maximum L2 norm, but so it's, what is R? R was this one, the maximum of the L2 norm of every element in A. Then now let's think about L2 norm of this element. Each component is either +1 and -1. So if you square each component, it's going to be always 1. And so each norm is going to be exactly m. Okay, I mean the square root of m. So in our context, this R will become square root of m. And what can we say more? Now if you look at the size of this H restricted to S, that is also very similar to the growth function that we designed. Growth function is almost like the size of H restricted to S, but we are taking the maximum over all these x1 up to xn. So this quantity is bounded by growth function of m. Because essentially the growth function is the same as, because growth function is really maximum. That's really the growth function is. Okay? So now if we replace these two into the formula, so then we get expectation over m 2 times log of growth function. And then what's going inside the expectation doesn't depend on the sample, so it can be taken out. Expectation of some constant is the constant. So this is m 2 times log of. So that's the proof of the corollary 3.8. And now because the corollary 3.8 is true, the theorem that I told you, the theorem corollary 3.9, which is a generalization bound involving growth function, is going to hold. So what are the key steps? The key step is we are using Massad lemma is the key step. Use this one. And then so using the Massad lemma, we in a sense kick out the distribution. So using the Massad lemma, still things are depending on the distribution. So we decouple the complicated quantity in the definition of Rademacher complex, empirical Rademacher complexity into the norm part and then the size part, the cardinality part. Then we just bound the cardinality with the growth function. In doing so, we make everything independent of the sample S, and then that gives us the upper bound. Okay. So then now the remaining question is how we can prove theorem 3.9. Okay. Okay, but before going there, let's just take a step back and think about the conclusion that we obtained. So the conclusion is what I told you before. So the conclusion is exactly this guy, number 3. And the conclusion say something like, we have a better generalization bound if our growth function start to deviate from this maximum exponential as early as possible. Okay, so if it grows slower than the exponential functions, so then we will have a tighter generalization bound. And then this slower growth than the exponential function really indicates our hypothesis class is limited. We cannot really express too many things using our hypothesis class. Now, for the entire story, what remains is to show the Massad lemma. And then the proof of the Massad lemma is, it's not difficult, but then it's essentially the application of so-called maximum inequality. And because there's really nothing other than just applying the maximum inequality, what I suggest you to do is just to have a look at what I mean in the lecture notes, okay? I think that what's written in the textbook, there's just some minor error. So just take a look at the lecture note. You will see that the a bit corrected version of the maximum inequality. And if you just apply maximum inequality, you will get a Massad lemma. More important bit is what Massad lemma allows us to do. It allows us to, we have a complicated supremum that involves size, which is y, as well as the cardinality. It intertwined these two things together. And Massad lemma allowed us to separate them out and bound the quantity, involving both sides and the norm, or cardinality and the norm, into something that talk about these norm parts and then the cardinality part separate. Okay. Right, so that's a generalization bound part. Now let's move to the next topic, which is the VC dimension. I think the VC dimension appears not just in the learning theory, but more generally. I heard it also appears in logic, study of the logic, as well as combinatorics. Okay. So what are the motivation of VC dimension? Here's a kind of recap of the generalization bound that we just proved. Say that the probability of risk bounded by empirical risk. Sorry, I think I should have used hat there. Maybe use so empirical risk. Yes. And log of delta is greater than equal to 1 minus delta. That's what we have shown. Okay. But now, sometimes the quantity that we have is good, but this growth function is not so ideal. Okay. Why that is the case? This growth function depending on m, but sometimes when we talk about the complexity of h, we want to come up with some concept, but that doesn't refer to m at all. So for instance, I showed you the picture. So if you look at the growth function, if the growth function is not really the exponential, it's really upper bound. It maybe in the beginning it starts to grow like an upper bound, but at some point it starts to deviate dramatically from this upper bound because of the limitation of the capacity of our hypothesis set. So maybe the large part of the information, although not all of them, large part of the information of the growth function can be captured by this deviation point. Yeah? So can we somehow just design something based on this deviation point? That's a fewer, not less information than the growth function, but maybe that captures enough, and then that maybe is much easier to deal with. So that's the motivation of the VC dimension. VC dimension is more approximate, less informative quantity than the growth function. But in doing so, it makes our life easier in terms of computation. VC dimension. we see dimension is just, it's like a dimension, which dimension is a single number, which can be either natural number or infinity. And that's, captures more approximate information than the growth function. So in some sense, it tried to capture the essence of the growth function without losing too much, okay? But what's really going on in the growth, what's captured by the growth function. So what is the Brice dimension? The Brice dimension is defined like this. So to define the Brice dimension, we have to first capture definition of shattered. We say that a set finite set x is 0 is shattered by h. So h is shattered by h if the following is true. And what I'm gonna describe now is really say, however you label the inputs in x0, we can classify that we can, we can achieve zero error by some hypothesis in H. Okay. Any labeling in over the inputs in x0, we can achieve a zero error. So that's what this shattered means. So that means for any subset x1, x2 prime of x2. Okay. So that's the subset we're gonna label positive, and all the rest in x0 will be labeled negative intuitively. So any subset x0, there exists hypothesis in H such that it's achieved zero error. What does that mean? x0 prime is exactly the same as input in x0 such that h of x equal to positive. That really means that we can achieve a zero error. So for this finite set, any labeling we can achieve a zero error by choosing appropriate hypothesis. So that's what shattered means. And then the definition of Brice dimension. Brice dimension. And this is a semi-formal of is the cardinality of a maximum shattered set. So the Brice dimension, it means the cardinality of maximum shattered set. Of course, there may be a case that with this maximum shattered set doesn't exist. The shattered set is a finite set. There may be the finite set of size 3, which can be shattered, 4 can be shattered, 5 can be shattered, and so on. So in that case, we said the Brice dimension is infinite. So the more formal definition is semi-formal, more formally. This Brice dimension of H is defined by the Spreeman of M and Spreeman of M such that if we can shatter some subset maximum. Okay. What does that mean? It means you compute the growth function at M that is maximum. So this equality means there exists some subset of inputs of size M that can be shattered completely by the hypothesis. So that's what this means. Also, in terms of the graph that I showed you, this really means if the VC dimension is finite, that means that that's the point that the growth function deviates from this exponential function, from the upper bound. So the key intuition here is that that point is a single number, but that point captures a lot of information about what's really going on. So that's the key idea behind the VC dimension. Okay, so then let me first tell you a few things about the VC dimension, and then just let us do the calculation about the VC dimension. The first thing is that VC dimension, suppose VC dimension of H is, say, 5. This doesn't mean that every subset x0 of size 5 can be shattered. By H. So it doesn't talk about every subset can be shattered by H. The supremum is ranging over this M. So it's a set. So we want to make this. We have a 7. We have this set here. So we are taking the supremum is over the integers. So we are taking this the maximum. So then the supremum may return the infinity. Okay, does that answer your question? Okay, good. So this VC dimension doesn't talk about every subset. It just talks about some subset. Some subset of size 5 is shattered. So don't be confused. VC dimension as well as the growth function, they are talking about the best possible scenario in terms of distinguishability. Okay. So that's the one thing that I want to notice. And then the other natural question is, suppose that VC dimension, which say 5, again 5. Does this mean that there exists a subset x0 of size, say 4, that can be shattered? In other words, VC dimension is defined by the maximum. Can any number that's smaller than VC dimension, can we find some subset that can also be shattered? And the answer is, yeah, that's right. Answer is yes. That's because if VC dimension is 5, you just pick some subset of size 5, x0 to x4. If you just kick out one element there, that will give us a subset of size 4 that can also be shattered. Okay. So the answer is yes. Now the third one, which we will show, is we introduced this VC dimension. Now, how can you use this VC dimension to get a generalization bound? And then the generalization bound we can achieve is the following. If the VC dimension is D, so dimension of H is equal to D, then this quantity can be bounded by this 2 log n. So everything is the same except that this growth function can be bounded by this first dimension, which is em divided by. Okay. So I mean, you may, so this D, I mean, this what this exponential is doing. This exponential is doing is that the growth, roughly speaking, these growth functions is a bit like a growing 2 to the, I mean, the worst case growing 2 to the m. Yeah. So this, I mean, this inequality is really coming from inequality that pi h of n is bounded by dm, d, and d. So really, it's they say that if we have a VC dimension, the VC, this growth function is not growing like 2 to the m. Its exponent is not m. Exponent is going to be bounded by d. Okay, so it's going to be polynomial. It's not depending on m. This d will be the degree of the highest order. Okay, and the second, if you see the proof later, you may see, okay, why this the e, which is, I mean, coming from this. I mean, I forgot its actual name. Why E appears? This E appears because of this, I mean, essentially a Taylor expansion of exponential function. So you have an infinite sum, but not exactly infinite sum, but sum of things. And that this E is really capturing this sum of many, many quantities. Okay. So that's the results that we're gonna get. Now, before going to the results, in our remaining 20 minutes, let's compute the VC dimension. Okay. So VC dimension, again, is the size of the maximum shattered set. Now let's start with the questions. Examples. So think about something very easy. So it's about, the first example is intervals. So what is the hypothesis class is an interval. And what is the input space? Input space, just a set of reals. And what is a hypothesis? Hypothesis is the function that maps input to if the input is between specific lower bound and upper bound, then we return 1. Otherwise, we return -1. And then L and R, they are just real numbers. So then the question is, what's going to be the VC dimension? So try to solve this. Okay. The second one is the VC dimension of hyperplanes. And the hyperplanes in RD. So what is the input space? Input space is RD. And what is the hypothesis? Hypothesis is mapping that takes input in d-dimensional Euclidean space. And then we take a sign. So, after computing inner products. So this is really, I will tell you geometrically what this means. And W is a b-dimensional vector. This bias B is just real number. And this is sine function. Say sine of some part sine of y is 1 if y is positive, minus 1 if y is not positive. And in the two-dimensional case, what this does is it's really we are drawing a line. I think W is the, the directions, like it's a normal vector, and B talk about how much this line is deviating from the origin, and by the direction of this W, what we are doing is everything that goes above is going to be marked as plus. Everything that goes below will be marked as a below and including the boundary is going to be marked as a minus. Okay. What's going to be the VC dimension of this? It can be used to classify things, but what's going to be VC dimension of H in this case? If it's very hard, the second question is not very easy. Okay, so for the second question, think about E is equal to 2 case, and then try to generalize the solution. So I will give you 2 minutes to think about these questions. Yes, so 7 is right for number 1. So it's related to the I think Rademacher complex calculation of the Rademacher complexity. And think about number 2. So it's actually number 2 is not. Showing the lower bound is easy. Upper bound is not super difficult. Upper bound requires some result about Euclidean space, some geometry. Okay, so the answer is number 2. My first answer is 2. Set. This is 2. And why that's the case? If you have just a line or 2 points which are different, then you can actually shatter it. So any sign you give plus, 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 minus, minus, plus, minus, minus. And what we can do is that, for plus, plus, we can think about the interval that contains both points, which is going to be this lower bound is going to be the beginning of the interval, the upper bound right of u is going to be the largest point of the interval. For plus case, we can give an interval like this, minus, and the other case have an interval like this. The last, we can just put an interval to the outside. So we can shatter it. But if you have a 3 points, then there will be a 3 points. And there is one labeling which we cannot shatter, which is both sides are plus, the middle point is a minus, then we cannot shatter because the interval should contain the first guy and the last guy. But then once you contain first guy and last guy, the middle guy should be there. So really the third one shows the limited expressiveness of this interval hypothesis class. Now for planes, this is a D plus 2, D plus 1. Okay. So D plus 1. And then let's think about the lower bounds, how we can show this VC dimension is greater than equal to D plus 1. That means just give one example which can be shattered. Also, we want to show this upper bound, especially want to show that it's smaller than D plus 2. Now, how to do the lower bound part? So the idea of the lower bounds, let me show this lower bounds with some specific example in the 2 dimension. So the lower bound is easy because we have a lot of freedom. We can choose, in these 2 case, we can choose the 3 points. Okay. In a best possible way, so that our hypothesis can classify correctly every possible labeling. Okay. So how we should choose the 2 dimension case? We're gonna choose the first point is going to be unit points. It's going to be x0. Second point is going to be everything is 0 except this x-axis has a value 1. So that's going to be x1. The third point is everything is 0 except the second axis will have a value 1. That's going to be x2. So we have these 3 points. Okay. Now, what we have to do is that for any labeling, we can classify everything in the labeling correctly. So in other words, we can get 0 classification error. So let's think about specific labeling here. For x2, say we want to say +1, x1, maybe we just said -1, x0, we want to say -1. So now how we can classify this systematically. One way to do systematically is to consider for x2 and x1, we are considering a direction for, so we are considering a direction but which collects these 2 points together. I think my explanation is not that clear. So for these 2 guys, what we're gonna do is that we will consider a direction which put these two things together, that's going to be plus, for x-axis, it's a -1, y-axis, it's going to be +1. +1 is coming from here, -1 is coming from here. Okay. So what that means, that our direction is going to be this. So we have this direction. And now for the last bit, it's -1. We will decide that we're gonna move this whole thing by, move it by -1/2. So the actual, the lines that we're gonna use is this guy. Yeah, I'm laughing because I thought this is more intuitive, but looks like it's not. X and Y. Yes. Sign. So this means that our line will be drawn on this side. So this -1 has the effect of moving towards this arrow. So we will have a line. It's not really a line. So we have a line that is perpendicular to the arrow we draw, but then because of -1/2, it's going to be moved to the other side. Sorry about this. I thought drawing picture in 2D will give you an intuition, but it looks like it's not. So the general construction goes like this. For the d-dimensional point, we pick for x0 is going to be everywhere 0. x1, they're going to be 1. x2 will be second coordinate is 1 and so on. And xd is going to be 0. Each one. So we have a d+1 point, and then y1 up to yd. And we're gonna define the w to be y0. No. y1, y2 up to yd. And b, we'll define it by y0 divided by 2. So if we do so, then this line, let's call it h of x, sine of w x plus b. It has this property. If we plug in x0, then this part will become 0 and only b remains. It's going to be sine as b. That is exactly y0. And wb, we plug in xi, where I is not equal to 0. So then this will be sine of, and only the yi part will survive here. y0. And that is because it's the yi, y0, they are both plus or -1, same as the sine of yi. That is exactly yi. So I think maybe doing algebra is a bit easier. So if you define function of this form, that will provide the perfect classification in this case. So this shows that it's at least d+1. Now in the remaining 3 minutes, I'm going to tell you why its upper bound is d+2. So that's related to the so-called, what's the name? I think it's a Radon's theorem. quotidian. So what does theorem say? The theorem said that if X is the subset of the dimension such that it has a d plus 2 point, so then there exists x1, x2, both of them are subsets of X, and they form a partition. So to this entire thing, and then the one intersection is empty. But furthermore, the convex hull of x1 overlap convex hull of x2. This shows the visit dimension should be smaller than d plus 2. It's a bit like the scenario that we discussed, plus minus plus scenario for the rectangle case. Okay, we have a bunch of points, but we say that in 2D, if we have 4 points, then we can find the x1 and x2 such that convex hull overlap. So this we can choose these two guys and these two guys. And convex hull is a line that they overlap in the middle point. But if that's the case, okay, and if the one side is labeled minus, the other side is labeled plus here, then we have no way to distinguish them, to classify this perfectly using a line. Because whenever we draw a line, put everything plus on the one side, it will always include minus there. So then this Radon's theorem, so let me give me 2 minutes. The proof of Radon's theorem is not difficult. The Radon theorem is, it can be proved by linear algebra. So what we are doing, so if we have this x, then suppose we are given x in the theorem, then we construct d plus 1 equations, so linear equation, over d plus 2 variables. So it's a real variables, alpha 1 to alpha d plus 2. So what are the equations? Equation goes like this, say, as equal to 1 to n. So this x is x1 up to xd plus 2. Right? And so this is d plus 2 alpha I xi is equal to 0. And then summation of alpha I is equal to 1 d plus 2 is equal to 0. So this alpha I xi is a d-dimensional vector. So this, although it looks like just one equation, this is actually a d equations. And this is one equation. And what does this mean? This means that we have d plus 1 equations over d plus 2 variables. So there exists a non-zero solution. Of solution alpha 1 to alpha d plus 2. Now, if then we can, we define, we pick only those things which are positive. Because it's non-zero, there must be something which, and also this is sum is equal to 0. There must be something which is positive. There must be something which is negative. So we define J1 to be index such that alpha I is positive, and J2 is an index where alpha I is negative. Then finally, if we set x1 to be xi with the index in J1, x2 and xi with the index in J2, then it actually satisfies the property that I described there. And then the number 1 and 2 are easy, right? These are coming from by definition. Number 3 is the one that's not easy, but for number 3, if we use, this equality, then one thing that we can say this, that we define beta to be J1. So then this one is the same as alpha I. So if we use this fact, then right there. So this equality, and then the other equality that we have here, then we can show this number 3 is actually is true as well. Okay. Sorry for going over time, and that's it for today. And so thank you very much, and I hope to see you on Thursday.